Alright, so for this problem, it is chapter 1, problem 18, and I'll just go ahead and read it. It says, a Lagrangian for a particular physical system can be written as the following expression. I'll write it up here. It's L prime equals, equals M over 2 times the quantity. Let's turn these off. I always hate that. Okay. Times the quantity A x dot squared plus 2b x dot y dot plus c y dot squared minus, and then this is the presumably the potential, k over 2 ax squared plus 2bxy plus cy squared. Okay. And it says where a, b, and c are arbitrary constants, but subject to the condition that b squared minus ac cannot equal 0. So I'm just going to write that in red. So b squared minus ac cannot equal 0. Sort of mysterious, but we'll get into that in a bit. What are the equations of motion? Okay. Examine particularly the two cases A. Okay, so there's going to be two special cases. I'll write them in blue here. So number one is going to be A equals 0 equals C. And case 2 is B equals 0 and C equals negative A. So something special about these conditions. Okay, what is the physical system described by the above Lagrangian? So what is the system it's describing? And then it show the usual Lagrangian for the system as defined by equation 1.56. That all the equation 1.56, I'll write it so you're not confused. It's just L equals T minus U. That's all. Okay. Is related to L prime by a point transformation, which there's the 10th derivation in this chapter. Went over that in much greater detail. Then it says, what's the significance of the condition? So what's the significance of this guy, this b squared minus ac cannot be equal to 0? What is the significance there? So this is a bit of a long one. We'll go ahead and get started. So we have our Lagrangian, our L prime written down already. And we have our three conditions. So we'll go ahead and just get straight into our equations of motion. So there's the Euler-Lagrange equations d dt of partial L with, let's do x dot minus partial L with respect to x equals 0. So first we'll start with partial with respect to x dot of this. That's just m, right? So I'll kind of highlight it as I'm going. So x dot, right? So this is just doing differential. It's just doing a basic derivative. So m a x dot plus b. I'm canceling out the 2 right away if you didn't notice. by dot. Okay, so that's our first one. Let's circle it. Okay, now we need to find the full time derivative of that guy. And that's pretty easy. We're just going to add m ax double dot plus by double dot. And that's our first one. Okay, now we're going to go into our partial of L with respect to x. So that's going to be up here. And that's going to be equal minus k over 2. And then 2ax, right? Plus 2by. And that's it, because our last term doesn't have anything to do with x. Okay, and then that we can cancel out the 2, so it's minus k ax plus by. And that's our second term. And so our first equation of motion, we can write the entire thing out. I'm going to kind of skip a step here. You'll see what I'm doing here. Okay, ax double dot plus by double dot, just for the differential equation. And it's minus a minus, so it's plus k over m, right? X plus b y. I divided out the m to get rid of the coefficient for the ODE, and that equals 0. That's our first equation of motion. And then our second equation of motion is going to be y. So we go d dt partial L with respect to y dot minus partial L with respect to y equals 0. And so if we go back, we need to solve this. And what's that going to be? So we have a m over 2, and then with respect to y dot. So there's a y dot here and there's a y dot here. So what's that going to be? That's going to be 2b x dot plus 2c y dot, right? Okay, so let's just write that out. So m over 2, 2b x dot plus 2c y dot. Just basic partial derivatives here. And then we'll take the time derivative of this guy, dl over dy del, okay, equals m bx double dot plus cy double dot. And that is our time derivative. Okay, now we need to get our del L over del Y. And that we get from up here. So let's do green. Okay, so with y, we're going to have this term. We're going to have 2bx and then 2cy. 2bx and 2cy with minus k in front. So minus k over 2, right? 2bx plus 2cy. There's a minus over 2 up there, right? Okay, I see it. There we go. Now, what comes next is we'll just take out all the 2s, so mine equals minus k bx plus cy. Great. And if we put them together, we have our second equation of motion, which, again, I'm going to divide out the m here just right away. Bx double dot plus cy double dot plus, right, minus a minus, don't forget that, plus k over m bx plus cy equals 0. And this is our second equation of motion. All right, so now we have our two equations of motion, and that's it. So these are pretty. You know, they look very familiar. There's just some extra terms. Well, we're going to look at special case number 1. Special case number 1 was a equals 0 equals c. So c and a are both 0. And what happens is you get this. So you get bx double dot plus k over m bx equals 0. We can divide out the b here. And we get x double dot plus k over m x equals 0. And then if you make omega squared equal k over m, then you have your, this is just a basic harmonic oscillator in the x direction. And then if you have our other equation, you get by double dot plus k over m by equals 0. You get the exact same thing, y double dot plus y, k over m, sorry, or omega squared equals 0. So we get our harmonic oscillator again. And So write that down. Harmonic, because what physical system? It's a harmonic oscillator in 2 dimensions, x and y. All right, so our special case number 2 is, what was our special case number 2? It was b equals 0 and c equals minus a. So we end up getting these equations. You get ax double dot plus k over m. If you go back up and you just substitute 0 for b, substitute c for minus a, that's all we're doing here. So km ax equals 0. Again, you divide out the a here and you just get x double dot plus k over m, x equals 0. And then you get minus a y double dot plus k over m minus a y equals 0. You can divide by a minus a here and you get the same thing. Y double dot plus k over m y equals 0. So this is where the point transformation comes in. So you just have these arbitrary constants where if you set them to 0, or if you set them up in such a way, you can retrieve your harmonic oscillator again. And that's the whole point. Now, if you go back to the equations of motion, I'm going to write them down one more time here. So a x double dot plus b y double dot plus k over m ax plus by equals 0, number 1. And then our second one is, where is it? Where did I put that? Okay, bx double dot plus cy double dot plus k over m bx plus cy equals 0. And then, just a moment here. So if we set this up, we can actually set this up like a matrix problem, where you have a plus, ax plus by equals u. And then we have bx plus cy equals v. And we can set this up like this. u v equals a, b, b, c times x, y vector here. And so this is going to answer the question of why we can't have ac minus b squared equals 0. It's going to answer this question because anytime you have a matrix like this, so you have a system of linear equations, which that's what these are, in linear algebra, for this matrix, to describe 2 degrees of freedom, which we have a 2D harmonic oscillator, the matrix has to be invertible. So that means the determinant of this matrix cannot equal 0. So what it's doing is it collapses the degrees of freedom into, you're getting rid of one of your variables, essentially. So you're collapsing it into just x or just y because they become dependent variables. Where if you want dependent variables, then this comes from linear algebra again, then this matrix has to be invertible, which means its determinant cannot be 0. So if AC were, so if you look at this determinant, AC minus B squared was 0, if these two were the same, then it would not be invertible. So that's the special case here with B squared minus AC. It is you have something physical, which is a 2-dimensional harmonic oscillator. And so if AC was equal to B squared, then it would no longer be a 2-dimensional harmonic oscillator. So that's what's giving it that restriction. So I hope that made sense. All right, that's it. Thanks.